Welcome viewers to the 9th lecture of the course Metal Cutting and Machine Tools. So, in this lecture we are going to cover some discussion on measurement of cutting forces, but previous to that whatever leftover portion was there for calculation of cutting forces, we will quickly have a look at that and then continue with the with today's discussion. So, to start with, in the last discussion that we were having, we derived the relation between the main cutting force P z and the shear component of the resultant force P s, P s along the shear plane, which is equal to P s, and therefore, P z was found to be P s into cos eta minus gamma 0 divided by cos beta plus eta minus gamma o. We had proceeded up till this, and then we replaced the value of P s by the shear strength of the material, dynamic shear strength of the material, and the area on which it is acting. The projected area we had found was equal to T by sin phi into S 0 sin phi. So, that sin phi cancels out. Let me just do it on here itself, that is this we can cancel out. So, that we have S 0 into T into tau s into all these trigonometric functions sin beta, cos beta plus eta minus gamma o and cos eta minus gamma o. The trouble is we cannot handle all these angles, because while we are knowing the value of gamma o is known from the tool angles, orthogonal rake, we do not have a concrete idea about what is the shear angle and what is eta. So, let us quickly go through the possible ways in which we can find it out. So, here this tau s, which is not known to us up till now, this tau s is actually taken to be assumed to have a relation with a constant value tau o, tau 0 plus its proportional part with the normal stress. How do we find out normal stress? We know the normal force on the shear plane, that divided by the area of the shear plane, that will give us the normal stress. So, that way if we divide, just let me go on to the next slide. So, just shifting the terms and getting an expression of sigma n in terms of tau. So, we also have a relation between the normal force, normal to the shear plane, and the plane and the force tangential to the shear plane. We have a tangential relationship by P n is here, P s is here, and this is the angle beta plus eta minus gamma o. So, we have a tangential relation between these two. So, if we divide it by the shear plane area, in that case we have sigma n replacing P n by area of A s is equal to sigma n, and that is equal to P s gets replaced by tau s in the process, and tan remains as it is. If we rearrange the coefficients and find out the value of tau s, because tau s is having one component from here and another component from here. So, if we collect coefficients and express tau s as a function of tau o, we get a relation of this type. All right. So, this is the constant of proportionality between the normal stress and the shear stress on the shear plane. Yes. So, if we do that, we can replace tau s in terms of tau o, tau 0, the constant portion of the shear stress, and this term appears at the bottom. This added term in the denominator appears. So, that the expression of P z is T s 0 into These things were previously there, cos eta minus gamma o, sin beta, cos beta plus eta minus gamma o. Additionally, this term comes in. Now, what is exactly the value of Pz? For this, we use the minimum energy principle, that is, in order for any process to be carried out, it will always follow the natural process of expending minimum energy to achieve that. So, if shear plane is creating the shear between lamina of the uncut chip, okay, it is getting sheared off, it will happen in such a way that minimum energy is expended. Otherwise, why should it go for any plane in which more energy is spent? It will go for that plane in which minimum energy is there, that will happen first. So, from the minimum energy principle, the least amount of Pz will define this particular plane. The least value of Pz occurs when this minimum energy is expended, because energy is equal to Pz into Vc. So, if we differentiate with Pz with respect to beta, we will be able to solve for that beta for which Pz is minimum. So, following that principle, if we differentiate, I have not included the whole mathematical derivation here. If you are interested, I will upload it in the form of a separate file, but believe me, if you try yourselves, I am sure you will be able to do it. That means, this particular expression, I am sure you will be able to derive it yourselves very easily. That is, if you try deriving this particular. So, here as you can well understand, all terms which are not containing beta, they will be treated as constants. So, you might be having only two terms, one is sin beta and another is cos beta plus eta minus gamma o, and of course, another term, that is 1 minus k into tan beta plus eta minus gamma o in the denominator to be derived. Okay. So, I am sure you will be able to do it yourselves. So, I am not including the formal discussion here. So, that finally gives us a relation twice beta plus eta minus gamma o is equal to tan inverse 1 by k. Now, what does this exactly mean? It means that the angles are going to have a relation in such a case, which case? For minimum energy to be expended to achieve chip formation. Okay. The angles are going to have this sort of a relationship. Is this the final thing in metal cutting? No. In fact, 10 to 11 different different types of theories are there, what can be the relation between these basic angles, and we are discussing just one of them. This is called Merchant's second solution following the minimum energy principle. Okay. So, that is equal to tan inverse 1 by k, where that is equal to cot inverse k, which is equated to a constant c, which is called the machining constant in some literature. So, that ultimately we can replace the relation between these angles in this expression. Now, if you notice this term in the middle, this term in the middle, it is equal to tau s, and if we keep it that way, we do not have to bother about the changes that will be happening due to incorporation of this relation here. So, we can remove it from consideration by just keeping the original value of tau s here. So, let us replace these values and see what happens. Yes, in that case we find that the expression comes out to be, all these things are untouched. This one, okay, this one expression since twice beta plus eta minus gamma O is equal to what is it called, C. Therefore, we can write beta plus eta minus gamma O equal to C minus beta, and therefore, we have replaced those values here. We have replaced that one here, beta plus eta minus gamma O has been replaced here, and it has been replaced here, all right. And therefore, after replacement, still we are knowing that this thing is equal to tau s, and we have straight replaced that formidably large expression here. So that we have left over sin beta here, cos C minus beta from the other side of the denominator coming here, and of course, previously we had cos eta minus gamma O here, which gets replaced by cos eta minus gamma O is naturally equal to C minus twice beta, that we have replaced here, and therefore, we get this particular expression. If you expand this expression, we will find that it will become equal to cot beta plus tan C minus beta, okay, cot beta plus tan C minus beta, and therefore, we can say that this expression will give us an estimation of the main cutting force P z. If we are knowing T we are knowing, of course, it is the depth of cut. If we are knowing feed we are knowing definitely in millimeters per revolution, it will be set by us only. If we know the shear strength, dynamic shear strength of the material, yes, that will be known. And of course, if this machining constant is found out by us, and of course, as I said, beta. Now, if you remember, beta, eta and zeta, they were related together, so that we can directly replace the value of beta here. Okay. So, I leave this to you, find out the value of tan beta, which we had found out to be equal to cos gamma O minus divided by zeta minus sin gamma O. If you put it here, we can replace beta as well. So, all the terms being known, we can find out the value of P z. If P z is known, we can find the value of P x y, and also we can find out the other values of like friction, normal force, F n and F and n, etc., everything can be known. So, we will have in the next lecture some numerical discussion of some numerical problems in which we can find out the force components of turning force components during orthogonal turning. Okay. Now, let us move on to the next subject of discussion. Yeah, the thing that we had proceeded to discuss today, that is the measurement of cutting forces. Why do cutting forces have to be at all measured? Is there any need? First of all, from a common sense approach, we can say that if we are measuring the cutting forces, and rather unless we are measuring cutting forces, how do we know all these discussions that we are having about calculation of cutting forces to be correct? So, in order to validate our calculations on cutting forces, we need to carry out experiments to find out whether we are really getting those forces as per calculations or not. But you might ask me, what is the whole point of calculating and measuring cutting forces? Suppose we know nothing about them, what is wrong? First of all, if we do not know cutting forces, we cannot estimate what should be the dimensions of the machine tool on which this cutting is going to take place. For example, suppose I am feeding a tool in the longitudinal direction with the help of a lead screw. So, the cutting tool is moving and it is experiencing feed forces actually to the feed screw which is making the carriage move. So, unless I know what sort of forces I am going to experience, how can I design the dimensions of this feed screw? So, for design calculations and other other activities, cutting forces will have to be known. You might still argue that the machine tool was already there on which you are using the cutting tool, but it is the everlasting question about which came before hand. Did the egg come first or the chicken come first? So, that way if you want to design machine tools, you have to know the cutting forces, you have to carry out the experiments. The experiments have to be carried out on a machine tool only. So, machine tool must be present, but in order to make the machine tool present, design has to be done. Okay, I mean a measurement of the cutting forces have to be done in order to design it, etc., etc. That is absolutely essential. That is knowing the forces through experiments in order to use that data for machine design. So many other reasons are there. I am not touching all of them, because these things I can give you references from which you can pick up this information. Acha. So, what do we exactly measure? Do we measure, for example, PS? Somebody is interested to measure PS, so that he can directly put it into the calculation of that merchant second solution, etc., etc., or PN. Generally, we are interested to measure, or rather we are capable of measuring forces in standard unchanging directions, and that immediately makes it clear that we measure it along Px, Py and Pz. Why do not we measure it along say the shear plane? That is because the shear plane does not have the same orientation in every case. So, that is out of question. So, standard directions are chosen for the measurement of cutting forces like Pz, Px and Py. So, next. How can we measure cutting forces? Cutting forces can be measured from elastic deflection. Now, what do we mean by that? We mean that if under the action of cutting forces, just a moment, if under the action of cutting forces this tool deflects, why should it deflect? Because the force is in the other direction. This force, mind you, is on the chip. The cutting tool experiences this force, because of which this is the force on the cutting tool. Okay? It deflects like a cantilever beam. My drawing is not very perfect, because it should have been here. Okay? Let me make that correction. This line is not supposed to be here. That is right. So, it deflects as a cantilever beam, and from the deflections we can find out the forces if they are within proportional limit. Okay. So, elastic deflections can be measured, and from that force can be estimated. We can have elastic deformation, that is strain. What do we mean by this? I mean that if there is a cantilever beam, and if this be the neutral axis, then we can estimate the strain here to be of tensile nature, bending of beams, and the strain on the bottom side is going to be compressive, and at the middle in the neutral axis there is no stress at all. So, that we can expect something of this type to happen. Stresses are like this, and I am just giving some arrows here to make you understand. So, it is reversed. On the top it is tensile, on the bottom it is compressive. So, from these strains we can estimate what is the force within elastic limit. Okay. So, we can also find out from the pressure. Okay. So, next let us see what do we have after this. So, first of all, if we want to measure strains, we can take the help of something called the strain gauge. How does the strain gauge work? The strain gauge, it's like I'll try to give you the idea in simple words. Suppose I have here a simple shaft, or say a rod of whatever cross section. So, this one I start pulling. If I pull it, it will undergo a strain. Okay. Now, in the same manner, suppose I have a body on top of which I have put a sort of conductor. It is absolutely cemented onto the body. If I pull the body is going to undergo longitudinal strain, and this body will also undergo the same amount of, whatever its length qualifies to, it will undergo strain. There will be no relative motion between the top surface and this particular element. So, it undergoes longitudinal strain. Together with that, it will undergo some change in the lateral direction also. But what do we achieve from that? We want to say that if it is undergoing a change in length, if it is say increasing in length due to tensile forces, and if its diameter is decreasing, if I measure its resistance, or say I measure the current flowing through it, I will be definitely able to register a change. So, from this change I can estimate what is going to be the what is the strain. That is what I will be estimating, what is the strain from the resistance change. If they are proportional, my work will be easier. It would be possible to extrapolate also, but the problem is how much should be this length? You will say 1 meter. I will say that is impossible. On the cutting tool, when the cutting tool is mounted on the lathe, there is hardly any elbow space. You have to do things within a very small space, but small spaces will mean that this length will be limited, and within this limited length you can hardly register, hardly expect some appreciable change in resistance to take place due to strain. So, what we do is, within a very small space, say this particular space is restricted within a few square millimeters. Okay. Maybe this side is say 4 millimeters, that size is 6 millimeters, like that. Within that, we enclose a large number of zigzag conductors. Okay. Some sort of pattern is chosen, so that the lengths are of a large quantity. What about this side? This side hardly there is any length, almost negligible. So, all these lengths add up. When the thing is stretched, okay, this is the thing, when the thing is stretched on two sides, all these lengths get stretched, so that within a confined zone of area, I will be having considerable change in the resistance due to considerable amount of strain getting registered. So, let us now see what happens after this. Yes. So, if we employ such strain gauges, due to stretching, longitudinal strain will change the length from L1 to L2. So, how do we estimate L2? L2 will be equal to L1 multiplied by, taking into consideration that epsilon 1 is the longitudinal strain. So, strain is defined as delta L by L, where L is the original length and delta L is the small increment in length. So, if we multiply it by the original length L1, we will get the corresponding change in length. Therefore, L2 is equal to L1 into 1 plus epsilon 1, where epsilon 1 is the longitudinal strain, that means in the direction of the stretch. We are considering for the moment that it is tensile stresses which have been which have arisen in the workpiece or the part under of our interest due to the forces which are applied, tensile forces giving rise to tensile stresses. So, this is tensile strain. However, if we consider if we assume we can generalize it also. If we assume that say the cross section is defined as a circular cross section of those strain gauge wires, in that case that will undergo generally a compression, but this compression is definitely not going to be following constancy of volume. Rather, from Poisson's ratio we will get a relation between this lateral strain and longitudinal strain. Lateral strain by longitudinal strain is equal to Poisson's ratio. But anyway, the new diameter will be decreased by original diameter multiplied by 1 minus epsilon 2. So, that is the lateral strain. Therefore, if we have the resistance to be defined as rho into L by A, we can differentiate this and get this particular relation between the differentials. Where do we, what is the origin of this one? This is simply resistance is equal to resistivity multiplied by length divided by cross sectional area. Resistivity for the time being we will consider to be constant. It is not affected by any of these physical phenomena which are occurring like stretching, etc. So, in that case, if we differentiate this, we will get dr by r is equal to d rho by rho plus dl by L plus dA by A minus dA by A, because it is in the denominator. This thing we will assign a value of 0 now itself. There is no change in resistivity. Hence, in the leftover terms, what we notice is that dl by L is nothing but the strain, and dA by A we painstakingly put in all the terms, so that we get pi by 4 into changed value of diameter square minus pi by 4 into d1 square original diameter. So, change in area divided by original area equal to epsilon 1, and naturally as d1 square is there, I mean d1 square, d2 square is equal to this thing, we get 1 minus epsilon 2 whole square, and from here we get 1. This thing cancels out, this thing will cancel. So, this is simply this term minus d1 square, what do you call it, this term, simply this term minus 1. So, that is what has come. So, if we increase it binomially and not even binomially, one if we say that this is a minus b whole square, the square of that strain term we neglect. So, that when we consider all these signs, out comes epsilon 1 plus twice epsilon 2. Okay. And hence, if we divide it by epsilon through the expression, we will get just a moment. Dividing the equation throughout by epsilon 1, we get dr by r by strain, that means change in resistance per unit strain is equal to 1 plus twice Poisson's ratio, because we will get epsilon 2 by epsilon 1 here, and that can be assumed to be equal to 2, which means that change in resistance per unit resistance divided by strain is actually a constant. These two things are proportional. Okay. So, this brings us to the end of the 9th lecture. In the 10th lecture, I want to exclusively discuss problems, numerical problems, and in the 11th lecture, I will be completing some part of the calculation on measurements, measurement of cutting forces, which I could not cover in this half hour lecture, but that part will not be included in the second week's syllabus. Okay. So, whatever I discuss on measurement of cutting forces in the 11th lecture will be treated as syllabus under the third week. So, thank you very much.